Welcome back, ladies and gentlemen. We're going to be continuing with organic chemistry. Specifically, we're going to be looking at hydrocarbon naming, right? So we talked the basics of organic chemistry. We talked about how organic compounds were originally thought of as things that could only be made by living things. Then Holler came along, German guy. Hopefully I'm pronouncing it right. He figured out how to make urea, part of P, from two inorganic materials, things he dug out of the ground. This was a big discovery, and it made us realize we had to really rethink this. But the idea behind organic chemistry was still important, so we kind of kept the name and a lot of the terminology just because it was so useful. So, as I sort of mentioned last time, we're going to be exploring the alphabet of organic chemistry. We're going to be exploring how to explain or describe things. Because this is sort of a very new field, or at least it is new for us. It's actually probably the oldest field in chemistry. This joke, if you want to call it that, is a science joke. And the rule of science jokes is that they're not funny. You're not allowed to laugh. Your response is either to go, huh, meaning you didn't study enough, or, in which case you did. Help save me, I'm dying! I'm trying! Let's see what these words mean. Okay, overview. The current procedure for naming organic compounds is based on a set of rules formulated by the good old IUPAC, the International Union of Pure and Applied Chemists. These guys are the ones who came up with the rules for ionic and covalent compounds as well, so you can blame them for all your troubles. The rules involve choosing a main or parent chain and then using a series of suffixes and prefixes to name the structure itself. So a prefix means it goes at the beginning, and a suffix means it goes at the end, or based on what you guys would see, beginning and end. Okay, let's do some examples here. Okay, there are three main types of hydrocarbon chains. Okay, so there's a chain, and then I'm going to put prefixes and suffixes. So the main chain is either going to be an alkane, an alkene, or an alkyne. You'll notice they're spelled almost identical, except that this one's got an A, this one's got an E, and this one's got a Y. Each has their own suffix outlined below, but all use the same prefixes. These prefixes indicate the number of carbons in the parent chain. You will need to know these prefixes. Okay, so we saw prefixes in ionic compounds, not really, but we did see them a lot in covalent compounds. Remember, there was mono, di, tri, tetra, penta. Same thing. We're going to have the same thing. If there's a bunch of them, we're going to use a bunch of different names. Now, unfortunately, organic chemists decided they needed to be different, so they didn't use the same names as covalent. Now, the reason for that is because that way nobody would get confused and try to figure out which one is this. But that means that we have an entirely new set of numbers to learn. I know. You can blame the IUPAC guys. Here it is. Meth, eth, prop, bute, pent, hex, hept, oct, none, dec. Actually, from 5 on, this is the same as the other set. It's only the first 4 that are different. Well, that's convenient. Meth. Yes, that is where the term meth comes from. The drug meth is so named because it's got some methyls in it, which we will talk about as we go through this. No, I won't show you how to actually make any of it. Sorry, guys. So here's some structural summaries, okay? We got some alkanes, some alkenes, and some alkynes. Down here we got another one called a cyclo. We'll talk about that later, but look at these. What do we see? This one is saturated. It's got all the single bonds it can have. This one has a double bond. This one, a triple bond. So what are we expecting to see here, right? Well, overall, we're expecting to see that those single, double, and triple bonds are going to be behaving in certain ways. They're going to be named based on what we observe. So that's why we have all these different sort of terms, these different words. Each of these words is used to describe a different kind of structure. You'll notice that all 3 of these, 1, 2, 3, have 2 carbons, 1, 2. In our previous list, what was 2 carbons on the previous list? F. Okay, F. This is an alkane. Ethane? prefix and suffix, put the two together. That's what we said we're going to do, right? Well, let's take a look. First one, alkanes. Saturated compounds containing only single bonds, straight or branch chains, it can be fancy or not, ends in ane. So, as I said, ethane. So that's our ethane. And, oh, we've got a general formula here. What does this mean? Well, take a look at the ethane over there. There's 2 carbons. How many hydrogens? There's 6 hydrogens. 2 carbons. 2 times 2 would be 4, plus 2 makes 6. So there's a pattern to how many carbons and hydrogens we're going to get in these different structures. This pattern we're going to see a little bit better once we get to the next one, alkenes. Alkenes, as it says here, they have double bonds. They can also be complicated or simple, and they end in ene. And you'll notice, hey, look, ethene. Same starting word, same prefix, because there's 2 of them. Eth was the word for 2. Ene means there's a double bond connecting them. Right? So the next one, before I even flip to it, it's going to have a triple bond. Triple bond, triple bond. There we go. Triple bond. There was alkanes, alkenes, alkynes. So the next one will be ethyne. Now it's spelled with a Y instead of an I, but that's because chemists are bad at naming things, but same basic rules. And notice, here it's just 2n. What do we see? 2 times n, well, if this is 2, 2 times n is 4, and if we look over there at ethene, we see there's a 4 right there. So that's exactly what we expected. Well, look at that. This next one here is going to be 2 times 2 minus 2. 2 times 2 is 4, minus 2 is 2. And then that's how many I get. And that would be ethyne. And it has a triple bond. Okay, so let's break this down. What are we seeing here? Okay, we've got our organic compounds. They have prefixes and they have suffixes. The suffix tells you how many bonds there are. Right? Are there triple bonds? There are double bonds. There are single bonds. Ein, ene, ane. The prefix tells you how many carbons there are. So a methane, meth is 1, so there's 1 carbon. An ethane is 2 carbons. A propane is 3 carbons. That word sounds familiar. If only we've heard it somewhere before. Maybe with a barbecue? The next one is 4. That's butane. Oh, wait, we've heard that one before too. That's a lighter, right? Now, none of you guys smoke, but a lighter is filled with butane. What's the next one? Pentane. Okay. That's 5. 6 would be hexane, heptane, octane. That's gasoline. All of these familiar sounding words are coming out. Who knew they were actually organic chemistry this entire time? Now, I did mention that there was an extra one, sort of alluded to it in the past there. There is a cycloalkane. These are saturated compounds that contain a ring. So basically, we took the long chain and we attached the 2 sides together. That's it. It's nothing fancy. Cyclohexane is over there. You'll notice that it's got the same structure as an alkene, right? N times 2, right? So N in this case is 6. 6 times 2 is 12. We have 12 hydrogens. The reason for that, of course, is because each one of those carbons has 4 bonds connecting it. Okay. So overall, this isn't, super complicated. This is how we can draw these things. These are how these things are categorized. So let's take a look at the naming rules. For alkenes and alkynes, the location of the double or triple bond is indicated by a prefix number. What? We have a prefix on top of a prefix? Why do we need that? Well, let's think this through. 2-pentene means that the double bond is located on the second bond. Okay, let me get out some markers here, just off camera, and I want to draw this more fully, right? We're going to use the complete structure. Heck, we'll use a couple colors. So, we need an eraser. So, pentene. So it's got 5 carbons. So 1, 2, 3, 4, 5. Okay, so we've got our 5 carbons. Now I'm telling you that there's a double bond because I'm telling you it's an ene, right? E-N-E ending means double bond. But where do I put it? Right, like I could put it here, and that would be pentene. It's got a double bond. There's 5 of them. But I could also put it here. That's also a double bond, and there's 5 carbons. So I need a way to tell the difference between where it goes. How do we do that? We put a number. 2-pentene means that it is a double bond on the second possible bond from the end. We count from the end. Why do we count from the end? Well, did you want to count from the middle? That's going to be really annoying. We choose an end. We start counting. So here's 1. There's 2. This is 3, 4, 5 in terms of the carbons. In terms of the bonds, this is the first bond. This is the second bond. So I put a double bond in there. Now, I shouldn't be lazy. I should put a few extra hydrogens in there too. Each carbon wants 4 bonds. So this guy over here has got 1 already. 2, 3, 4. I've done it in blue for the hydrogens. 2 bonds here, so I need 2 more. 1, 2. This guy has 1, 2, 3, so it only needs 1. Same with this guy, only needs 1. And this guy over here needs 3. So there we go. There's our structure. Now, over here we've got a sort of condensed form, and over here we've got just a pure line diagram. We talked about those last time. Remember, it's when the chemists get really lazy and they don't want to have to draw any more symbols. And each vertex, each corner, is a carbon, right? So we have a carbon here, 1, 2, 3, 4, 5. And they just don't bother drawing them, and they don't draw the hydrogens because they're just sort of looking at it going, look, look, look. I know you're an awesome chemist, and I'm clearly an awesome chemist, which means that we totally understand each other and that there should be a bunch of hydrogens over there, but we are far too busy to draw all of them. Whether or not that's true depends on how much you've practiced. Okay. Oh, I should probably erase some things here because these are in the way. If there's more than 1 double or triple bond, then we use Greek prefixes to indicate the number and place it just after the organic prefix. So we've got some options here. There's more than 1. Okay, what are we talking about? Just after, wait, what? Just after the organic prefix? Okay, let's get out some other colors here. Let's take a look. There's a lot to take in. First things first. You see here, there are 2 symbols, right? There's 1 and 4. So that means there are 2 double or triple bonds. Which one is it? Oh, look at the ending, right? The ending here is E-N-E. E-N-E means that there is a double bond. But there's not 1 double bond, there's 2 double bonds. There is a double of double bonds. Why? Because they tell me 2 places it is, 1 and 4. Okay, let's not panic, break the problem down. First things first, it's got penta in front. Penta in front means 5, so I probably shouldn't have erased it. 1, 2, 3, 4, 5. Okay, we got our 5 carbons. That part was easy. Then I've got an E-N-E ending. E-N-E means a double bond. And where do I put the double bond? I put it on the first one and on the fourth one. Okay, so let's say I start counting from here. I could count over here. I could count from either side. That's fine. But I'm going to count from here. I'm going to put a double bond here. That's the first one. 2, 3, 4. Right there. So there's my double bond structure, right? We've got double bonds on both ends. We got one here and we got one over there. Now we just got to put in our hydrogens. I'm going to get the blue again. This guy's got 2 bonds, so he needs 2 more. 1, 2. This guy has 3, so he needs 1. This guy has 2, so he needs 2. This guy needs only 1, and this guy needs 2. So there we go. There is our 1,4-pentadiene. Wait a second. I said di in there. Di. Mono, di, tri. Di means 2. How many double bonds do I have again? 2. So what they do is, if there's more than one double bond, right? If there's only one double bond, they don't say anything. They just say En, E ending. But if there's two double bonds, they put a die in here. And they put it in the middle rather than the beginning because they want to confuse you. Did it work? Probably. So if there were three double bonds, right? I'm going to make one up here. If there were three double bonds, let's say there was, I don't know, 1, 2, 4 pentatriene, right? Because there's three double bonds in this case. Where do I have to put the next double bond? 2. I decided 2. I made up this question. I made it 2. If you don't like it, make your own question. This is my question. So now I got to change the number of double bonds here. Because look, I put an extra bond here. So this guy here now, this carbon's got 1, 2, 3, 4, 5. I can't do that. So I'm going to take one away. This guy here's got 1, 2, 3, 4. So this is gone. There we go. We're done. Okay? So this is sort of the rules about how we assemble these things. We've got to take the picture and we've got to figure it out one step at a time, right? So we see here it's 1, 2, 4 pentatriene versus 1, 4 pentadiene because there's 2 of them. Here, there's 3 of them. Okay, I hope that makes sense. It's a lot to keep track of, but in terms of the actual rules, it's not too bad, really. I mean, it's using stuff we already know, right? We already know all about the the covalent prefixes, right? Mono, di, tri, tetra. We've now learned a new set of prefixes, right? Meth, eth, prop, bute. Why did they use them? History, mostly. They already had the names. They wanted to keep them. Here it is. I don't know. Nothing fancy to it, really. All right. So right now you guys have some practice that you guys can try. Okay. And I want you guys to attempt that practice. I don't remember what page it is in your book. That's fine. You'll check. It's the next couple pages. I'll make sure to note down the questions. But right away, right, once we get through the basics, it gets more advanced, right? Of course it gets more advanced. Not everything's going to be simple. It's not all ABCs. You got to start putting them together. Got to make something more complicated. So naming rules do grow more complex. No surprise for anybody. Straight chains. We already talked about straight chains. That is just one chain that starts from here to there, right? We saw all these penta chains, all these 5-member chains. They just started from here and they went all the way to the end. Very simple. This is a straight chain. This is propane, right? Prop. Meth, eth, prop. Prop is 3. Propane, because there's no double bonds. Branched chains. We've heard these before. What does branch mean? Like, where have you heard branch before when it comes to describing something? Well, that would be like a branch of a tree. And what happens when you have a branch of a tree? They separate. That's a lot more words. It's a lot more letters. But it's not so bad. Take a look. Right down here, there's propane again. It's still there. What does that mean? Meth, eth, prop. There are still 3 carbons in a row somewhere. We can see them. 1, 2, 3. So what have I done is that I've added 1 extra carbon in the middle. Well, what do we call 1 carbon? Meth. And look, right here, meth. And where did we put that 1 extra carbon? On the second spot, right? 1, 2, attach the extra one. So the second spot has a meth, and the rest of it is a propane. So in total, if I were to pronounce this word, it would be 2-methylpropane. And that's it. That's how you would describe this. So what's that O part, the YL? I guess we'll have to explore that. We'll have to figure that out. But what we can see is that all of these words are assembled piece by piece, like Lego. You can blame the Germans. The German language is very good at combining words like this, and they do it all the time because their language is just naturally like that. And at the time when a lot of this organic chemistry naming was being finalized, the Germans were big in it. They were the ones really pioneering everything. So they came up with all the rules for naming it, and they were like, well, our language does this all the time, so everyone can do it, no problem. So that side chain, that branch, is called a substituent. It's a weird word. It just means a side chain. So when naming a branched chain alkane, a substituent can take the place of a hydrogen atom on the parent chain. Parent meaning, of course, the big one, right? Parent chain versus child. A hydrocarbon substituent, a side chain, is called an alkyl group. Just because. It's got alkyl in there, right? ALK is part of alkane right here. Whoop, you can almost see it if I don't cover it up. Alkane right there. So an alkyl group is just changing the ending from ane to YL. So we're changing the suffix again. We're always just changing the suffixes and the prefixes. Basically, alkyl groups are alkanes that replace a hydrogen on the parent. Right? We saw that in the last slide. For side chains, the usual ane ending is dropped for the YL ending that we've already seen. And this is just a way for us to say this is a side chain, not the main attraction. This is a sideshow. This is the child of the parent by putting the YL on it. Why they chose YL? No idea. So for example, meth becomes methyl. These are the three options that we're going to see: methyl, ethyl, and propyl. You may recognize some of those words. Like if you get rubbing alcohol, the label will say that it is rubbing alcohol. It will also say that it is isopropyl alcohol. There's propyl in there, propyl. Ethyl is just 2. Propyl is just 3. So the IUPAC rules for naming branch chains are quite straightforward, but they're very detailed. It's sort of one of those, like, it's got a checklist that you got to work your way through. Okay, so we're going to do this one. This is 3-ethyl-2,4-dimethylhexane. Okay, there's a picture of it. See if you can map out what the rules are going to be, okay? But we're going to break this down. We're going to work this out one step at a time, okay? Let's take a look. Find the longest continuous chain of carbon molecules. That is the first step, okay? We need to figure out what the biggest chain is. That's the parent. We need to figure that out. Now, we already know what it is because I just told you. It's hexane, so it's going to be 6, okay? So now we look here. This chain is used as the parent structure. In this example, the longest continuous chain contains 6 carbon atoms. I think I highlighted it? No. Therefore, the parent hydrocarbon structure is hexane. Okay, so if I look here, if I cover it, this could be considered a single longest chain. Right? There are 6 carbons there. Now that I've circled it, I think hopefully you guys can see with more clarity that there are a couple little branches that stick out, like boom, boom, and boom. There's the 6. We circled them. Number the carbons in the main chain in sequence so that the side chains are closest to the start. So I can number either side. I could say this side is 1. I could say that side is 1. Right? I can count either way. But if I count from this side first, this is 1, 2, 3 before something interesting happens. If I count from this side, it's 1, 2, and something interesting happens. Less steps, that's what we're going to go for. So that side over there is 1. This side closer to me is 6. In this instance, the numbers go from right to left, which places the substituent groups, the side chose, at 2, 3, and 4. If the chain were numbered from left to right, the groups would be at 3, 4, and 5, which isn't wrong, but it's not right. It's, again, in the analogy of like trying to have a conversation with somebody, if you number this backwards, it would be like you go to somebody and you say, I hello you. Technically, all the right words are in there. Technically, you're not wrong, but it's weird because that's not how the English language works, or doesn't work, depending on how you want to look at it. So there are certain rules that we follow for this particular thing. They're arbitrary. They're just there because that's what people decided, but they're part of the language of chemistry. These are higher numbers and therefore violate the rule of counting them out. Okay? Use the numbers to indicate the location of the side chains and prefixes to state the composition, basically how big are the side chains. So for example, much like how we marked double triple bonds with numbers, we mark the position of the side chains with numbers. We also use the prefixes to describe the individual parts of the chain. So in this example, the side chains are located at 2, 3, and 4. There is a 2 that is a methyl. There is a 3 that's an ethyl. And there's a 4 that's a methyl, right? Because the 3 is the one that's too big, so it's ethyl. And the 4 and the 2 are both methyls because they're one big. Okay? So far, so good, I hope. 4. Use prefixes to indicate if a group appears more than once. What do I mean by that? Di, tri, tetra, penta are going to be pretty common. We've seen these, right? In this example, there are 2 methyls. So rather than write 2-methyl, 4-methyl, we write 2,4-dimethyl. So we're saying there are 2 of them. Basically, the chemists were lazy. I don't want to have to write out 2-methyl and 4-methyl. Can I just can I write less? Can I just say di to say 2? Because I don't know di. Di is part of my lexicon. It's part of the language of chemistry. I already know that word. Why don't I just use it? So they were lazy. They decided to use it. Finally, list the names of the alkyl substituents in alphabetical order. For the purpose of alphabetizing, the prefixes di, tri, and so on are ignored. So we don't care about that. In this example, 3-ethyl group is listed before the 2-methyl and the 4-methyl, which, as we just said, are combined into 2,4-dimethyl because E comes before M in the English language. Oh, this is a lot, and then I got to use proper punctuation. This is like I'm writing a full sentence here. This is very important when writing the names of organic compounds with the IUPAC system. You put commas to separate numbers and hyphens to separate numbers from words. The net result of this is that you write the whole thing as one word. There is no spaces. Thus, dimethylhexane, not dimethyl space hexane. All together. So, when we put all of these rules together, we get 3-ethyl 2,4-dimethylhexane. It's a lot, I know. Again, I'm going to go through it one step at a time. I'm going to run through it. Now that we have it on screen, we can see it. We find the parent chain. It was 6 big hexane. Okay, hexane. We got that. There were 3 side chains. This one, and this one. They're located at positions 2, 3, and 4. The chains at position 2 and at position 4 are identical. They're both 1 carbon big. In our naming rules, that's a methyl. But there are 2 of them. So that is a dimethyl, or 2 methyls. Now we have to put all that information in there, and we put it in alphabetical order. So ethyl, starting with an E, comes first. So it is 3-ethyl. Then it is 2 and 4 are where the dimethyls are. There are 2 methyls. They're located at 2 and 4. So it is 3-ethyl, 2,4-dimethyl hexane. It's a lot. It's a mouthful. It is a lot to keep track of, right? Like, individually, each of these steps is not hard. Count the biggest number of carbons. That's not hard. How many side chains are there? That's not hard. There's 3. How big are they? Also not hard. This one is size 1. This one is size 2. This one over here is size 1. Also far, that's not hard. Where are the side chains? They're located at 2, 3, and 4. Also not hard. Are there any doubles? Yeah, I've got two methyls, so they're dimethyl. Put that whole thing together. It's one word, dimethyl, two methyls. Where are the two methyls located? At 2 and 4, right? Right here, 2 and 4. Where's the ethyl? It's at 3. Then the last rule, commas between numbers, hyphens between numbers and letters. Make it all one word. Individually, each step is not hard. There's just a lot of steps, and they're very picky steps. So if you miss a piece, it just is a headache. We're going to need a lot of practice on this. We always do, right? We're learning a new language, and like learning any new language, the first time is always very painful. Okay? So let's take a look here. Oh yeah, here the whole thing is all in one place. Summarized. Let's get rid of this circle. Here it all is in one place. So try these. Okay? We know our rules. Okay? Step 1. Let's look. Step 1, find the longest chain. Okay. Longest chain. Got our marker. Here we go. Longest chain. 1, 2, 3, 4. Okay, that's 4 long. 1, 2, 3, 4. Okay, that's 4 long. 1, 2, 3, 4. That's 4. 1, 2, 3, 4. That's also 4. So far 4 is looking pretty likely, but you'll notice I'm checking every direction because you never know. 1, 2, 3, 4, 5. Okay. This was the longest chain. Okay, on the plus side, we now know what it is. It's 5, right? I counted it. It's 5. So I can write down that word immediately. Pentane. Okay, 5. 5. I can count. Can you? Hopefully better than me. Pentane. We've got 2 side chains. They're located at the carbon 3. Doesn't matter which side I start at. 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5. So they're both at 3. Okay, so at 3, I'm going to have not one chain, but 2 chains. So there are 2 at 3. Okay. What type of chain are they? They're methyls. And there are 2 of them. So it's dimethyl. And then I put a hyphen. So this one would be 3,3-dimethylpentane. There are 2 methyls. They're both located at position 3. And there are 5 carbons otherwise. Okay, let's try the other one. Longest chain. Do we have to do some fancy, some zigzag thing? No, we don't. Not for this one. This one's pretty easy. You just go right across like this. It's another one with 5, right? 1, 2, 3, 4, 5. Okay, that makes it simple. And I've got how many chains sticking out? I've got 4 different chains sticking out. See, I even did 4 right this time. The chains, the side chains, the substituents are located at 2 and 4. 2 different places. But how many side chains do I have? What type? Well, they're all 4 are methyl side chains. If they're all methyl side chains, then this is still going to be pentane. But there are 4 of them. So it's going to be tetramethyl. Tetra is 4 from the covalent bonding rules. And those side chains are located at 2, 2, 4, 4. Two, 2, 4, 4 tetramethylpentane. Now that's a mouthful. And there it is, written in red and much better writing. This is going to take some practice, but on the plus side, when you're doing your practice, you guys will have your rules in front of you. You can look at them, you can check things over, make sure you're doing it right. You're going to notice that, unfortunately, your notebook does not have answers for every single question listed in the notebook. There is an answer key, however, it is online on the drive. You can check it there. I have it all drawn out. Okay? So you can see what the answers are. Don't worry. Now, continuing the pattern here for drawing, if I give you the name, you should be able to draw it. And part of the thing is that because all these different chemicals can have so many different structures, that's why the naming rules are so specific. Because that way, if I give you the name, you know what it looks like. Like, literally, you know what it looks like. Watch, 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 watch. Okay? Here, these are the rules. We know how to do this. Look, I'm going to show you. Okay? 2,2,4-trimethylpentane. Lots of words. Break it down. First step, look at the ending. Pentane. Okay? Pentane's at the ending. We know what to do with pentane. That's 5. Okay? So 1, 2, 3, 4, 5. Okay, that part of the word is done. We figured this part out. There we go. This part's finished. Let's look at the rest of it. 2, 2, and 4. We now know where the side chains are. They're on atom 2, 2, and 4. So that means this is going to be, okay, let's start counting. I'm going to count from here. So this is 1, this is 2, 3, 4, 5. At 2, there is going to be a side chain. At 2, there's another side chain. And at 4, there's a side chain. There you go. Side chains are always carbon, so I stick them on like that. What type of side chain, right? Is it a big one? Is it a small one? Okay, well, look. This part of the name, we've finished that. We're running out of stuff for us to look at. Trimethyl. Tri means 3. Methyl, these are just methyls. They're just one carbon. Okay, so I'm going to use the blue to mark how many hydrogens I have now, because I've got enough carbons. So there's going to be 3 hydrogens here. Here I've got 3 bonds already, so there's a 4th one. Here I've got 1 bond, so I need 3 more. 3 more. 3 more. Here in the middle I need 2. This guy's got 4 already. 1, 2, 3, 4. So he's done. This one here needs 3. There we go. We've drawn it. Yeah, I haven't written H's, but I'm using blue marker instead. Okay, so what do we have to do when we're turning words into structures? Unlike with ionic bonding and covalent bonding, where we kind of had to just sort of guess what they looked like, we just know. It tells us in the name. It is specifically done this way to make sure that you can draw it the moment somebody says the name. Now, that said, you still need to know the rules to be able to do that. Like, if it doesn't make sense, if the rules don't make sense, you look at this and you're just like, oh, I got no idea what any of that means, then yeah, it's going to take some practice. But it's the same as learning any language. It takes practice. There it is. This, of course, is that sort of line diagram style. And this, well, this is the full line. This is the condensed line structure. And this one here that I drew was sort of the full structure. Again, reminder, each one of the little points, each one of the little vertices is another carbon. So what we're saying here is that there's like 1 carbon here, 2, 3, 4, 5. And then there are 1, 2, 3 methyls that are kicking off at 2, 2, and 4. Okay. I know this is a lot. A lot. You guys are going to need a lot of practice. And there is a lot of practice. So this particular video here has covered a ton of things. We've covered lots of different rules. We've covered all the naming rules. We talked about anes, enes, ines. And I really hope you paused the video and tried some of the practice then. Then I showed you guys the more complex rules when it comes to side chains, whenever the chain is a little more complicated than just one line. So then hopefully you guys can do some practice with that. And now you've also seen what happens if you've got the name and you've got to turn it into the picture. And you saw, of course, that the name to picture part's actually pretty easy. Right? Name to formula, that's actually pretty easy. It's the formula of the name that's got so many steps. There's so many rules. So you guys are going to need some practice on this. I want you guys to do that. And then what you guys are going to see, of course, is that next time we're going to talk about isomers. We mentioned that word, but we're going to talk about it in more detail. Right now, you guys have a lot of practice to do. So I'm going to leave it there, and I'm going to see you guys next time.